Temas interesantes, público, participantes. Fíjese que hemos abarcado temas de datos abiertos, temas de legalidad, y vamos ahora con una charla tremendamente interesante desde Países Bajos. La charla será en inglés. Básicamente es un tema muy importante en el mundo de la ciencia de datos y es optimización in data science. Now we continue with our second day in the first Data Science Congress. Now let me present to Dr. Abel from Netherlands. He told us about important topics that combine optimization and data science. And now let me introduce Dr. Abel. He is an optimizer and applied mathematician. He has a PhD in nonlinear optimization from the State University of Campinas in Brazil. And he was professor from 2015 from 2021 at the Federal University of Paraná in Brazil. Currently, Dr. Abel is research software engineering at the Netherlands eScience Center, co-creator of the Julia Smooth Optimizer organization. Julia is a programming language for data science. Dr. Abel is co-creator of the CIDAMO, Data Science, Machine Learning, and Optimization Group in Brazil, and he is a YouTuber mostly talking about the Julia language. Abel has been involved with optimization in the Julia language since 2015. Dr. Abel, for us, it's a pleasure to stay with you today, and welcome to our first Data Science Congress in Colombia.
Hello, thanks for having me. I just received the presenter rights, so let me share my window. Okay. Let me know if you can see it.
Okay, perfect. We see your screen. Thank you.
Okay, great. Thank you. Thanks a lot for having me. Today I want to talk about a bit about optimization, mostly comparing to AI, and I want to talk about the Julia programming language as well, which I have been involved for a while. Okay, so thanks a lot for the presentation. Professor Wilmer, it was a great presentation. I can skip most of this. Just want to bring attention to some of these points. While I was a professor in Brazil, I mostly worked with the industrial mathematics program, and my most common disciplines were optimization, scientific computing, and data science. And I used the Julia programming language for most of that, almost everything that I did for my research, for teaching. Also during that time, I co-created the CIDAMO group, which is a data science, machine learning, and optimization group. That this group still has monthly meetups, so you can check the website or the LinkedIn for the group and to follow the meetups. They are in Portuguese, of course. And I'm also the co-creator of the Julia Smooth Optimizers organization, which is where most of my research has been. My research has been in nonlinear optimization and using the Julia programming language. We ended up creating this organization, this ecosystem of packages, and I will talk a little bit about it later. I'm a YouTuber, as has been said, and I'll just say like and subscribe. Okay, so I want to start by talking a little bit about modeling. This is not an optimization exclusive thing. You have a real problem that you want to solve. And to solve that real problem, find a solution for that. One way is to create a model by making some assumptions, making simplifications to your real problem. That model is easier to solve, so you can solve that model in many ways. Just some basic algorithms or methods, or maybe something more complicated like AI or optimization. And when you have the model solution, you go back to the real problem and try to interpret the solution. Maybe there's some deployment to be done. And finally, you go back to the real problem to see if the solution that you have is a valid solution, if it makes sense. And the idea of this modeling framework is that you're going to iterate on this. This is a loop. You're going to do a few iterations of modeling until you have something valid. Okay. I'm going to talk mostly about one specific aspect of this loop, which is the optimization part, but I'll do that in the context of modeling first. I'm gonna define optimization in a very simple way, so we don't have to go into any mathematics for a while, which is that we have a set of options and you have a way to evaluate these options. And with that, you want to choose the best one. For instance, you have stocks and you can choose how many of each stock you buy. You have a limited amount of money, so you have to choose which ones you buy, how much of it, and which ones you won't buy. So you have a limited amount of options. You have a way to evaluate them, which can be, for instance, you want to minimize your risk or maximize your expected returns. So you have an optimization problem. There are other names for this kind of optimization. You will find this normally as mathematical programming or decision analysis, which is a bit broader, or operations research, which is, I think, one of the most common names for this. I'm going to give you an example, which I like a lot, is the selling art on the beach. I have a YouTube video, again, like and subscribe, but I'm going to give you a simplified version of that. And the problem is the following. Javier is a student. He decides to drop out of college and to sell his art on the beach. And the art that Javier produces are necklaces and bracelets, and using beads and strings and whatever. And the question that Javier wants to answer is how much should he produce in a weekly basis. So we're going to model that. So we have to make some assumptions. Our assumptions will be that Javier works 40 hours a week, that he can produce one necklace in 5 hours, and he's going to sell that for 20 euros. He can produce one bracelet in 3 hours and sell that for 10 euros. And I'm going to assume no cost. So everything that he sells is profit. So we don't have to worry about that. For this simple problem, you can plot the whole problem in this graph. Have the number of bracelets and the number of necklaces. You can plot the constraint that we have, since he only works 40 hours a week. Javier must limit his options to this time limit line here. So everything inside this triangle. And also all of his choices must be integers. So the only thing that he has to worry about are these green dots, right? The integer possibilities that he has to solve. So these are our options. These are our choices. Now we have a way to evaluate them, which is just the profit that he's going to make with this sale. So for instance, if he sells one bracelet and 2 necklaces, he's making 50 euros. And also if he sells 3 bracelets and 1 necklace, he's making 50 euros. So on top of this line with a 50 on it, he's making 50 euros of profit. So these lines are sometimes called isoprofit lines. But if you have multivariate calculus, you know that these are just contour lines of a function, the function profit for these 2 variables. And having these isoprofit lines and all the choices, you can verify that the best solution is this one, 160 euros of profit. And that happens at this corner for 0 bracelets and 8 necklaces. And just a glimpse of how this works. The best solution here was found by moving the isoprofit line up to the last point touching the feasible set. The feasible set is the set of all choices, all possibilities. So we go back to Javier and we tell him, hey, we have found a solution for your problem. Just produce 8 necklaces, sell them for 20 euros, make 160 euros. That's it. And does it make sense? So we go back to the original problem. Javier says, well, I tried that, but I only sold 4 necklaces, so it doesn't work. And so we have to evaluate why it doesn't work. And we eventually figure out that we have made a wrong assumption, which is that we sell everything that we build. And that's an implicit assumption, and that's usually where a lot of the errors come from. This assumption is a kind of a strong assumption. So we have to go back to create a better model. And our new assumption now is that we have a demand and that we know this demand and that it follows this line. So the demand of the necklaces and the bracelets are linear functions of the price of those items. And you can see here in this plot how much he would sell for each price. So for 20 euros, he would sell the necklaces, 4 necklaces. If he decreases the price to 10 euros, he would sell 13 necklaces. Having those two things together, you can now also do the multiplication of them. So if you select, for instance, I want to sell 8 bracelets, the best price to sell the bracelet is also in this line. So you can multiply these two things, which is 8 and the price, and you get this plot, which is the discrete version of a parabola. For each quantity sold, how much profit am I making if I build only that item? And if you look individually at the items, you have the solution for Javier's problem. You can see that you can just build 8 bracelets and 11 necklaces, but unfortunately, this solution is not inside our feasible set. So this solution is out here, and it would be the best profit, but it's way, way out of our triangle. So we have to go back to the isoprofit curves. In this case, they are ellipses. And these isoprofit curves, you do the same thing with them. You just move them until you find the choice that satisfies the maximum profit that you can make, which is this one, 280 euros. And I like the solution because it also showcases that this problem is a bit harder than expected because it's strictly inside the feasible set. So this point here also means that Javier will have a few extra hours of sleep because he's not going to be working 40 hours a week. In practice, what you have is a bit more complicated than that because Javier, and it's not going to be a person, it's going to be a company. So you have to deal possibly with hundreds of products. The demand might change over time. This is a frequent situation because you don't sell everything, you don't sell the same amount every week. If you have a vacation period or if it's on the beach, if there is sun or not, will influence how much you sell. And your problem might also be bigger and include transportation and storage, for instance. So this kind of optimization has a lot of parts that you have to include in the model. So that's why it's a whole field of study and not just a simple toy problem that we are doing right now. So all of that to say that optimization is hard. You need to do what we have done. You need good data because you want to trust the data that you have. So of course it needs to be clean, but you also need to make sure that it's relevant. You need a decent model, so you have to do a few iterations to get to the good model. And you also need expertise, so that means you need to hire someone that knows how to do this modeling, knows how to identify the errors with the model, knows how to implement that for the computer to solve it. And in addition to that, it is also normally hard to solve an optimization problem like this one. We just show a very easy case where you can solve it graphically. If this was just a little bit more complicated, you could still just enumerate every possibility and solve it by brute force. But in practice, you will need some smart methods. So that's where the optimization methods come. And even then, it might be very, very hard, and you might have to buy a license to use a proprietary solver. And solver is just the name of the optimization methods. So it's like really hard to do optimization at a high level, like at scale. And just to be clear here, what I said with optimization versus AI, I'm mostly simplifying this part, which is just this modeling kind, which is mixed integer programming. And the second one with the demand is the nonlinear programming problem versus using data science, which would be in this case, you just say, okay, I have all this data and I want to predict the profit. So I'm just gonna do some model and try to guess a bunch of columns, create a bunch of new columns, a bunch of new features, and hope that my model does its thing. One approach is a bit more hand wavy, just I'm gonna put all my effort into creating a bunch of columns and hoping that scikit-learn will solve everything. And the other approach is the exact solution for the problem that you're modeling. So it requires a bunch more expertise on the problem, not on the implementation, just the packages that you're using on a language. So that means all of these things together mean that the barrier to enter optimization in industry and also in theory is larger. You need to study a lot more than you normally do for the basics of data science. Of course, I'm coming from academia, so and I have taught data science, so you can teach data science at a high level, at a PhD level if you want. But you see also a lot of people selling you the idea of boot camps, so you can do a bit of pandas, data frames, and try to solve the problem of your employer. But in practice, you need a bit more like of that. But specifically for optimization, you need a bunch of background, mathematical background for the modeling part, which makes it even harder than just implementing things and understanding the problem. So you need to understand the problem, the mathematics, and the implementation. Also, the barrier for companies to use optimization is harder because you need to hire someone for that specific field, which is not so much in vogue right now. People are moving away to AI in general or data science specifically. And also you might have to pay a lot of money for a solver, which might be a barrier for many companies that just want to make a quick profit. So those are a few of the reasons why you see a lot more data science and AI nowadays. When I started all of these, we of course already had machine learning, you already had neural networks, but most people were still strongly suggesting and using optimization and specifically MIP in the industry, and of course a lot of statistics as well, which is what we are always calling data science nowadays. So all of these goes back a long time into what has been called the 4 types of analytics. And that's also another reason why optimization is hard. So this is a simple description of analytics, a simple split of the analytics field, I guess. The first one is descriptive analytics. So you're trying to say what happened. So you need dashboards or reports or some kind of logging. The second kind is diagnostic, which is saying why it happened. So you first need to know what happens for you to answer why happened. And then you go to maybe some hypothesis testing, some root cause analysis, some inference maybe. Those two things together are sometimes called business intelligence or business analytics. When you have that, you can then move to the next one, which is predictive analytics, which is what will happen. Predictive analytics is where most of the data science that we hear a lot about happens, for forecasting being one of the main things. So that's why I use the heavy rain forecast there. But you can think about demand forecasting, which is predicting what the demand will be. But also classification is there. So if you want to predict if a client will leave the company or not, predict the engagement of users in your website, things like that. After all that, usually is when you go to prescriptive analytics, which is telling you what you should do. You kind of need everything else to come before for you to talk about that. What to do with all that information then. And just so we can have this example that I showed a bit more concretely, we used this, which was Javier said, hey, the sales are low, which was really easy to figure out in this case, no dashboard required. Why that happened? So I just jumped already to the solution, which was we had wrong assumptions. With that in mind, we said, and I just, again, skipped all of that. There is a demand. So how do we figure out the demand? Well, a lot of method would be involved into figuring out the demand. You do some kind of forecasting. We figured out that it was a linear demand that we just used. And after all of that was done, we could optimize and have our solution with the extra constraints that we created, with the extra assumptions that we had for the model. So this is the common example of the analytics. On the other side of optimization, and this is usually a kind of a different field inside optimization, you have a more, sometimes more theoretical, sometimes more mathematical, in the sense that you are not exactly looking at a problem anymore. You're more looking at just, I have a mathematical expression that I want to maximize or minimize with some constraints that are also mathematical expressions. And the best example that I can give you in this context is machine learning, which has a lot of that. So when you're using any of the machine learning methods, you're doing a lot of optimization. I like this linear and logistic regressions example, which are just maximum likelihood estimation, and the maximum is in the name, so it is optimization. These are related to the normal distribution and the Bernoulli distribution, so it's like immediately translated into a mathematical problem that you have to compute derivatives and whatnot. Another example that I like a lot of us in optimization like the support vector machine, which is a bit more graphical, but we also like it because to get to the real way of solving support vector machine, you have to understand duality theory, a little bit of it at least, which is like a hard topic inside optimization. So this simple problem, which is just quadratic, linear constraint, convex, actually requires a lot of optimization theory in it, and I guess that's why, as professors, we like that. And of course, you have neural network, the most simple case being the multi-layer perceptron, which is just a function with a bunch of matrices and activation functions being applied over and over. And it is a very hard problem, non-linear with multiple local minima, right? So optimization is also required in this other field, and it's a different kind of optimization, but also inside the whole optimization umbrella. So AI and optimization are essentially linked. That's kind of my takeaway for this part of the talk. And this brings me to the next part of the talk, which is the Julia programming language. So what is Julia? Julia is an open source language, which means I'm not trying to sell you Julia or anything. I'm not the one involved in building Julia at all. It's a high level, high performance language. So high level is a relative thing, means it's easier to read than lower level languages. So if you compare it to Java and C++, it's much easier to write and read the code and execute usually as well. So it's much more like Python, R, and MATLAB, but it's high performance because it is compiled, and so we can get as fast or close enough to Fortran, C, C++, and Java in many situations. So that's why usually we say that Julia solves the two-language problem, which is when you have to prototype in a high-level language and you have to make a performant version when you want to deploy, when you want to embed this somewhere. There are companies that are investing in Julia because of this, but I also think of it as a really good investment for students, especially if you're starting your research right now. A lot of people in my university, so like I use MATLAB for my classes, And then I started using C++ for my research, and a lot of people did that. So we had, for instance, a master's using MATLAB, but for the PhD, you would need to do something with C++ or Fortran because it needed to be competitive. And so you would essentially implement the same thing twice. And Julia is a great solution for that, so you don't have to implement things twice. Very quickly, Julia is just-in-time compiled, and Julia has something called multiple dispatch, and you don't have to worry about those things. I'm just saying for completeness, let's keep that. So Julia is free, accessible, easy to install and to use. It works on the major operating systems. It has good development interfaces. So VS Code is the main one. You just install a Julia plugin and you have this interface here, which is kind of like RStudio or the Spider interface or MATLAB interface as well. But you can also use it from the notebooks. So you have the Jupyter notebooks, which I imagine most of you have heard about. The Jupyter, the Ju in Jupyter is from Julia actually. So it's Julia and Python here. I think you also have some terminal and R involved, but yeah, the Ju is the part that interests me at this moment. And you also have another notebook in Julia, which is the Pluto notebook, which is a bit different. I'm gonna quickly show you later. Julia also has built-in environments and a package manager. So if you ever had to install things in Python and you had a lot of things to do, like you have to install pip and conda or poetry and whatever, Julia solves that in a very nice way. It's all built in the language. Everybody uses it. If you want to build a new package, you have to use it. So everybody's aligned in that and everybody likes it. And the other good thing about Julia is that it's dynamically typed and it has type annotations, which means you don't have to give the types. So you can just say x equals 1 and it works. But if you want to give the types, you also can, and those types will be respected. They will be checked. So in a compiled way of thinking about it, they are respected. Another good thing about Julia is that it's friendly for mathematical stuff. So this is because it's based on MATLAB a little bit. So it's amazing for linear algebra. So here I am creating a matrix A and a vector X. And here on the right, you're seeing a quick example of a linear algebra evaluation, which is you create a B vector, which is A times X, and in Julia is exactly the same, A times X. Then you solve a linear system to find Y, and to solve a linear system, you use the backslash A backslash B, and that's it. You just compare both of them, X minus Y, and compute the norm, which is also very simple to interpret from mathematical notation. So it's great for linear algebra things. Another example, so I'm showcasing a bunch of Julia stuff here. So you have a function named Gram-Schmidt for the Gram-Schmidt orthogonalization process. You have the projection function here, which is another way to create functions. This has the projection of V in U is the dot UV times U divided by the dot UU. And if you look at this definition here, this is exactly what you have in there. The dot UV times U divided by the dot UU. And so it's really nice to interpret that. Here for this, to access the column name number K of a matrix E, you can just say E column K. And this line here is implementing this definition, which is VK minus the sum of the projection of VK onto EJ. I'm using E because of efficiency reasons. For J in 1 to K minus 1. So the summation is pretty easy to understand as well. So it's an easy language to read, not only in general, but also mathematically. And the other thing that you might love or hate is that Julia has Unicode characters and actually also has emojis, but that's a different thing. So you can, for instance, define function names using Unicode characters or variable names using Unicode characters. So here is this plus minus AB is a function, and this function just creates A minus B and A plus B. So you can just say 2 plus minus 03 and it works. Here is nabla f, which is just the name of the function that's computing the gradient. So this is not special in any way. This could be written like gradient f if I wanted. But if I use nabla f as a mathematician, I know what I'm talking about. Everybody that reads this and knows about this understands the code. And if they have also an understanding of the Newton method, this line here is pretty clear. You can just subtract this system solution using the Hessian and the gradient. That's the Newton method. Another example, you can use Greek letters like sigma to create, this is the sigmoid function in a single line with a if else. Oh, sorry about that. You can create y hat. In this case, I'm computing the prediction, so y hat is what we usually use for the prediction. Lowercase l in this case, and it's very nice language to read. And also Julia is fast. So when we talk about Julia being fast, we are mostly talking about being comparable to compiled languages. So these are compiled languages, and you can see that they all are around the C speed for most of the benchmarks that we have. And if you look at interpreted languages like MATLAB, Python, and R, they are usually slower, up to sometimes 100 times lower, can be worse in some cases. This is an older benchmark, so you should definitely benchmark your own use cases. But the main idea for me, the best thing for me, also as a research software engineer, is that if I have a slow code, I can make a slow code in Julia. That is possible. You can definitely do bad things. It is easier to make that Julia code faster than it would be if I had a Python code, for instance. So one thing that we do here at the Netherlands Science Center, if you have a Python code that needs to be faster and it's not possible to do it in Python, you can use C++ and call C++ from Python. But that means you have to learn a little bit about C++ and you have to glue the two things together, which is not very nice. So it's easier to just make Julia faster than to make Python faster in this case. And by the way, when you think about the main stack of scikit-learn, the pandas, NumPy, etc., a lot of that code is C++. So the Python stack for data science is actually a lot of C++ going on in the backend. So that's why I like Julia. This is another benchmark that I have. This is from a blog post that I made 1 year ago, maybe 1.5 years ago, which is Python calling NumPy here in black. Then you have a bunch of different versions of Julia code, and you have here, this line is the C code. This is all relative to C++ time, so C++ time is 1.0. But the main thing here is that this is Python calling those things. So Python calling pandas, Python calling Julia versions, and Python calling C++. So what I think it's important to take away is that it's easy to get a good Julia version. This pre-alloc Julia version here, which is pretty decent, like at most 3 times slower than the C++ version. And it's even possible to get a Julia version that is even faster than the C++ version. But of course, this is optimized Julia code. The C++ code was not optimized. It was done in the past, so you could make them comparable. Another thing that is less interesting for data science people just using things, but maybe for some of researchers might be interesting, is that Julia has native integration with Fortran and C. So if you have like a Fortran, this is a C definition of a Fortran function. You can easily call that function from Julia. If you understand the C code, this is easy to read. And this was essential for me. This is the reason, one of the main reasons, probably the most important reason for me to use Julia back in 2015, which I had to use the Fortran package Qtest to test all of the optimization code. So this working made the whole ecosystem that I talked about possible. Finally, we get into the optimization in Julia. There are a lot of packages in Julia that I'm not going to go over. There are machine learning packages. There is the MLJ organization, which does a lot of machine learning, like you have scikit-learn. You also have Flux, which is for neural networks. But since I'm not an expert on those things, I will focus on optimization in Julia. And for that, I will talk about two ecosystems, not just packages. Jump being a package and an ecosystem, mainly for modeling. So all of that modeling that we did in the beginning is Jump. So you write it in a very nice way. You write the equations, and then you give those equations to a solver. You use classic solvers for that. So if you use other modeling languages like AMPL, GUMS, GLPK, and whatever, all of those languages integrate with these solvers. And Julia is not different. It works with those solvers as well, like Gurobi, Cplex, and HICE, IPOpt. And so you're not losing a lot, but by using a modeling language on top of a programming language, in addition to being free and open source, you also have all of the other things that that language provides. So you can do plotting, you can add a graph, you can do a bunch of stuff that the language provides to you as well. And just a disclaimer, I am just a user of Jump. I do know the developers a little bit, and I did work a little bit with them in the past, but I'm mostly a user. So I'm not selling you in the sense that I'm gaining anything by telling you to use Jump. On the other hand, I am gaining something when I tell you to use Julia Smooth optimizers. This is my research, so of course there are other ways to do optimization in Julia, but I like this one better. So the main objective of Julia Smooth optimizers was to provide researchers in nonlinear optimization with a good way to create new solvers. We focus on pure Julia solvers. So if you want to create a new solver or use a solver to solve a problem, you can come to Julia Smooth optimizers and find something there. And as I said, I am one of the founders. We are not selling you anything as well. These are all open source packages that you can just download and use. But of course, what we like is if people do use them, they can contribute back, they can come be part of the community. And that's what I gain if you do use Julia Smooth optimizers. I gain a stronger community. Okay, so now is notebook time. So let's hope that nothing breaks. This is the live demo part. So if you ever heard of live demos, you know they tend to go wrong. So let's hope it doesn't happen. This is the Pluto notebook. So most things in Julia have these three colors somewhere. So you can see this is a Julia thing from the colors. It looks like a normal notebook. One big thing is if you use the packages here, they are automatically installed. So you don't have to separately install them. One cool thing as well, you can just do math here. So like, let's say I have z equals 1. And you can just say 2 times z minus 1. If you change the value of z, everything that uses z also changes. So this is what is called a reactive notebook. So it's really useful because then you are making sure that you're not missing any cell or deleting something that shouldn't be deleted, and making sure that it's always reproducible. So this is a great way to make a reproducible demonstration of your package. So I'm going to delete this because we don't want to see that. So this is the first example that I showed before. I'm creating a matrix A here. So this is a matrix in Julia. Then I have a vector X. When I multiply A times X, it just computes the value B. A backslash B solves that. And the norm of X minus Y is this thing, which is something times 10 to the minus 15, which is a very small number, which is close enough to 0. Numerically, it is 0 for all intents and purposes. Another example, so this is a random matrix in Julia. So SPRAND is for sparse random. This sparse matrix is being represented here. We can't see everything because we don't want to see 1,000 by 1,000 matrix on screen. If I multiply the matrix by the transpose of the matrix and a sum I, which is the identity, this is what I get. So this nice matrix, I can do the same thing as I did for the main dense matrix above, and it works. Again, a very small number, right? Julia is very extensible. So one cool thing that you can do is you can create new structures and you can expand a lot of the functions for these structures. So here I have a normal, which has a mu and a sigma. So this, of course, is a structure to hold the normal distribution. Notice I'm not saying anything special about this. This is a Julia thing. I'm saying that whenever I create a normal, by default, use the mean 0 and the standard deviation 1. This is the PDF of the normal, so the probability density function, which is that exponential with a bunch of things. You don't have to worry about that. The CDF, which is the cumulative, is just the integral of that PDF from -infinity to x. And this is where the cool things happen. I can define what happens if I try to add two normal distributions. So if I have a D1 and D2, what is D1 plus D2? And here you have the definition. The mean is the sum of both means, and the standard deviation is this square root of the squares of the other two distributions. And same for multiplying by a value. So this allows us to, bunch of spoilers here. Let's do this first. So I'm also plotting the distribution here, but just assume that it works. So this is one of the distributions that I have down here, D1, 1.23, and this value, just so it looks nice. And I could, for instance, multiply this by 0.5, and it works. Immediately, it's understood that this is now another mean and another standard deviation. And this also allows me to create two distributions. I'm going to plot them both. So these two here. And I'm going to create the convex combination of them. So multiplying one by a value t and the other one by 1 minus t, and I'm summing them both. So here for 0, nothing happens. I just have this green stuff. But when I move this, you can see that I have the combination of both of them. The average is just, the mean is just the convex combination, but the standard deviation has a little bit of nonlinearity, which is nice. And by the way, this thing here is part of the Pluto UI, the user interface that you can quickly add. Another cool example is, since Julia allows for a bunch of composability, is very expressive, there is a package called forwarddiff that can compute a derivative of almost any Julia function. This is just a bunch of multiplication, a sign. I can add exponential here if I want. Probably good if I multiply by 0.5. And all of those things are differentiated at a value x, which is another function. And I can even compute the linear approximation at a point A. And this is what you're seeing right here. When I move this, the position of the linear approximation changes. But this is all computed in Julia. And it's not an approximation of the derivative. it is using derivatives using is computing derivatives using something called dual numbers, which is in mathematical terms very cool. Finally, another basic example. I said I was going to talk about optimization, but I like this example because a lot of plots. This is the heat on a plaque, a square metal plaque. This is showing the heat over time with some heat source on this side here. And the basic idea is that this is all basic Julia. There is no package being used here. I just compute the discretization by hand. And here I am updating it. Very basic stuff just to show the plot essentially. Finally, this is another notebook for the jump. So going back to our initial example, we have two items, bracelets and necklaces. Then I have the time to build each one of them, the profit for each one of them, the demand and at 0 and at the decay of the demand, and a lot of functions to plot the stuff. And we can go back to this soon. This is jump. So I'm creating a model. This model thing is a jump thing. Highs is one of those solvers that I said is an external package that solves optimization problems. I have a variable called units sold for each item that I have, how many of those I'm going to sell. Remember, this is without the demand assumption. So units sold for bracelets, units sold for necklaces. My objective is to maximize the sum of this product, which is number of units times the price, which is the definition of profit, assuming no costs. And here I have a similar thing for the constraints of hours. So the amount of time that I take to build those things must be limited by the available hours, and just plotting stuff here. And this is the solution. Similarly, if you have the other case, the main thing that changes is now we also have another constraint, which is the demand at 0 minus the demand is limiting the number of units that I'm actually going to sell. So it's really easy to write this. I'm not going to show the mathematical equations behind them, but they are essentially exactly the same thing. And just to show that you could quickly change this, I can say, hey, I'm also going to work on Saturdays now, so 48 hours, and check the solution has immediately changed. It's a small problem, so it's very easy to solve here, but the solution has changed in both situations, right? So jump is very expressive. I do recommend you take a look into that. But finally, trying to sell a bit of my packages. This is the JSO packages. I'm mostly worried about just a function or a function and constraints. So I have an optimization function here, which you don't have to worry where it comes from, but it's a very classical one, the Rosenbrock. And you can just define it here. So you say, this is the objective. This is where you start looking for it. Use LBFGS, which is a very well-known solver. Solve that and give me the solution. And you can see the solution of this problem is 1, 1. Not very fun. Let's show a more visual example. So I have created some random data for you. These are data for classification. Doesn't matter how I created them. And I'm going to model the logistic regression for this problem. So I have sigma. And by the way, I have skipped this, but to write a sigma, you can just say sigma tab, and it writes the sigma variable for you. So sigma of t is the logistic function with some checks to make sure it's numerically stable. Then I have the loss function, which is the log of the Bernoulli discrete distribution. I forgot the name of this. It's not continuous, so it has a different name. And the log becomes this expression. except for this epsilon, which is also for numerical stability. Did I mention I like scientific computing? So those things are very close to the mathematical definition. This is the model that we're going to use. The model is the logistic function applied to a linear combination of the features and independent term. And this is the loss function, which is just summing all of the losses. And since I want to minimize, I have a minus sign here, which is the minimum instead of the maximum, but of a negative value, which is the same thing. So all of this, by the way, is just Julia. There is no package involved. Now I have a package which is ADNLP models, and this package allows me to create a problem, giving only the loss and where to start looking for it. So if you have a good idea, just give it. Otherwise, you are starting from zeros. Solve with LBFGS, and down here, I'm just plotting the solution. And you can see that it is a decent solution for this problem. And again, just to show that you can change this, I'm gonna add another few terms, which is the square of each one of the features and the mix the feature as well, essentially changing the problem to be a quadratic model inside the logistic function. So I'm gonna wait a bit so I can play here. And very quickly, all of this fails because I failed to change this to 6. This is, like I said, sometimes things happen. And this is the solution. Right, so again, now it's a quadratic function inside the logistic. So the boundary of our thing is ellipses, right? And essentially, that's what I wanted to talk to you about. There are many more things that you can do with Julia Smooth Optimizers, but I wanted to showcase a very simple example. And I'm coming back to my slides just to say, you can check more of my stuff on abelsiqueira.com or get in touch with me. And thanks a lot for having me.
Dr. Abel, thank you for your time and for your knowledge. Honestly, the Julia programming language is new for us in Colombia. I am not sure in Latin America. We have a lot of questions, and let me select some of them. Basically, we have one important question, and why should we use Julia over R or Python?
You mean why use one or the other? Is that the question?
Yes, maybe what is the benefits they use Julia against R or Python?
Great, a great question, which is one of the most common questions that I get.
Yes.
So there are good reasons to use all of these languages. I'm not a R user, so I can't talk much about it. I do know it a bit. Python has a lot of benefits. So if you want to do something that is established, like 30 years of Python already, you want to be able to easily find a lot of the documentation. Python is a great language. If you're developing something new, or if you need a lot of speed because what you're developing is not included in any very fast Python package, Julia is a great language.
Okay.
So for instance, if you're doing research, if you're developing a new method, if you want to test things, Julia is very good to use in that case.
Okay, perfect. Thank you. Let me ask another question. Basically, can Julia models be implemented in Android or other technologies for front end?
That's a good question, but I don't know because I don't know a lot about Android. So yeah, I'm sorry, I can't answer that one.
Okay,
I mean,
perfect.
natively, I know that can't, but I mean, I'm not an expert, so.
Okay, Python is a very popular language in data science, basically due to the wide range of packages, for example, Pandas, TensorFlow, and so on. How does Julia compare in this regard about the libraries?
Yeah, it's also a bit of that that I just answered for the comparison. Julia has packages for that, so you can even use scikit-learn from Julia. It's kind of easy to do, but of course you have to relearn a lot of the things, so not clear advantage there. What Julia has that is very big is in the field of what's it called, physics-informed neural networks. So let's say that you have a differential equation and you want to use a neural network on top of your differential equation. So you don't have an explicit model, you're training something, use a lot of hard mathematics on top of that. So Julia has the whole flux and diff-ACK, the whole SciML, to be explicit, is very strong in Julia. So for instance, just some examples. These are not my examples at all. This is part of the SciML. So you have a few of the, well, at least one of the Formula One companies using Julia to simulate, I guess, wind or whatever other conditions for the cars. So that involves a lot of differential equations. It needs to be fast, and it needs to use some neural network. So that's one of the places that's being used.
Okay, and the last question is, Rust is a programming language, and Manuel asked that at the moment is receiving a lot of attention compared to Julia. Do you know information about the comparison between Julia and Rust?
A little bit. So from what I have seen, and Rust is still on my list of languages to learn, Rust is a little bit more low level. It's the barrier to learn Rust is much larger. It feels more like C because you still have to do a lot of well, anyway, memory is involved, so it's always harder. So that's a big thing. And Rust doesn't have a lot of things also when you want to do linear algebra related stuff. So like things exist, but they are not really already polished for that. So if you're developing things like you would for C, C++, they are really low level. Rust is an amazing language, and Julia will be for things a bit more high level, from high level coming down. So I like to think, and this might be just wishful thinking, that we eventually are going to move from Python and R to Julia being more forefront, and we're going to move from C, Fortran, C++ to use a bit more of Rust. So Julia and Rust will actually be used together in the future.
Okay.
Hopefully.
Dr. Abel, thank you. To finish, we are delivering some books of this data quality, and can you help me please with what number? One moment, let me share because we are delivering some books during the participant of the Congress, and please, could you give me a random number from 1 to 210, please?
I can. I'm gonna use Julia for that. So random number from 1 to 210?
Yes.
Okay, it's number 10.
Okay, one moment, please. Let me find the number 10. Okay, number 10. The participant is Carlos Perez, the winner of the one exemplar of this book. Dr. Abel, thank you for your time, for the opportunity. For us, it's an important your presentation.